Good evening, everyone. Am I audible? Can anyone confirm?
Yes, ma'am, you are audible.
Thank you so much. Good evening, everyone. My name is Neha Yadav, and I will be your host for today's session. And I think we should wait for 5 minutes so that everybody can join. And I kindly request you all to complete the poll which is given in this session. Do you guys find the poll? It is at the right corner. If anybody find difficulty, please let me know. I can help. Yes, Pradeepa. I think you have raised your hand.
Yes, ma'am, I'm not able to find the poll. Can you please tell me where it is?
It is at the right bottom.
Okay.
Yeah, the triangle shape and the rectangular.
So anyone who is using a mobile, he will find or she'll find the three dots in the bottom side.
Yeah.
It's the three dots vertical. Click on that three vertical dots. In that you will put activities there. Right? So you can click on activities and then there is a polls. So you can, just give some small questionnaires to better understand your, type of audience that we have. So that's the poll.
Okay, I think everybody has joined the session. So let's begin. On the behalf of scholarscolab.com, it is my absolute pleasure to welcome you all to this highly anticipated webinar on advanced graphical deep learning into healthcare industry. Before we begin the session, I kindly request you all who are participating in this workshop, please complete the poll. And this will enable us to gain a deeper understanding of our audience and help guide the direction of this webinar more effectively. So about the workshop, as technology continues to evolve, the integration of deep learning models in healthcare is transforming the way we diagnose, treat, and manage diseases. One of the most innovative areas of this transformation is the use of graphical deep learning, which leverages the power of graph structure to model complex relationships in healthcare data. These advancements allow for more accurate predictions, smarter diagnosis system, and improved patient care. Today marks the beginning of a transformative journey into the potential application of graphical deep learning in healthcare. We are laying the foundation for groundbreaking research, and in the coming days, we will be diving deeper into the subject with a detailed workshop that will cover the entire project. The workshop will be held on the 8th of December, coming 8th of December. The workshop will walk you through a comprehensive literature survey, code implementation, and Python based code description, ensuring you to get both the theoretical and practical insights into this cutting edge technology. Come to the today's webinar. We will be diving into how graphical deep learning can revolutionize the recognition of depression from EEG data, an area that is gaining significant attention in both research and practical applications. Before we start uh, with this content, I would like to inform you that the code for this research project is available for free in our website and will be shared in the chat shortly. Coordinator, please share the code in the chat section. Moving forward, we are honored to have some of the brightest minds in the field with us today, ready to share their expertise, insights, and vision for the future. Allow me to introduce our esteemed speakers who have graciously joined us for this session. First, it is my honor to introduce Dr. Prateek Bindra, the project manager of scholarscollab.com. Dr. Bindra is a distinguished researcher with a PhD in nanoelectronics from BITS Plani and postdoctoral experience from KU Leuven, Belgium. Over a decade of experience in semiconductor research and development, his contributions have significantly advanced the field. Dr. Bindra has also served as a faculty member at NIT Jalandhar in JNU New Delhi, where he has been instrumental in nurturing the next generation of engineers and researchers. His leadership in various R&D projects further highlight his commitment to innovation. Dr. Bindra is the head coordinator of both this webinar and the upcoming workshop. He will also explain the future possibility that you can gain from participating in this webinar. We are delighted to have Dr. Bindra with us today. I now invite Dr. Bindra to deliver his insightful talk. Please, guys, join me in giving him a warm welcome. Please welcome, sir.
So thank you, Neha. Thank you for your kind words. So I welcome you all our participants who have joined today for this webinar. So in this webinar, as you all know, the topic of the webinar is graphical deep learning in the healthcare system, right? And we already know that the graphical deep learning has proven very worth in the diverse healthcare applications like, drug delivery, like predictive models, medical images. So you have a brief introduction in this particular webinar where we will see how this graphical deep learning is paving path to detect depressions using EEG signal, right? So we will see how EEG signals can be used with your graphical deep learning to detect better the depression in any humankind. Fine. So you will see that one particular IEEE transaction paper, we will see how the people basically done this particular research. Fine. So the idea is to just because this audience is of different domain, right? So the idea is to just show you a bit of the possibility that what graphical deep learning can do for your different applications. Fine. So it is not again confined to a particular application. So because you all people are of different domains, I guess. So but how this graphical deep learning can be helpful to in your research. So that's what we want to showcase in today's webinar. So, and about our company Scholars Collab, right? So we are just it's kind of a our nurturing phase. So Scholars Collab is particular domain where both the scholars and the faculties have some contribution to our platform, right? So we are basically an online platform where your experienced researchers can use their mentorships, use their expertise, and connect with our juniors researchers, and they can provide the mentorship to our junior researchers. They can also upload their published codes or their research work on our website, and they can also get some monetization support whenever someone download their product, so he or may get some monetary uh, benefits also. So for the experienced researchers, this is a platform where you can showcase your research work to a larger audience, right? So we welcome all the mentors who are currently in the webinar. So we welcome them. Then you can just join us as a mentor. You just simply go to the website, and you can have all this particular detail in our website. And for the researcher or for the young students or engineering students or science students, for them, again, you can find our platform where you can find some centralized research codes, which can be very verified codes, which is helpful for your research. So you need not to be again do the same coding. So our platform provide the some of the already published research codes, which will be helpful to accelerate your research. Fine. So I again request you all to go to our particular website, and you can find more information about our company. And I guess again the idea is to increase the productivity of the research. Fine. And we are just want to have a channel where the people of different domains, of different intellectual people, right? So come and share their knowledge. Fine. So coming back to this webinar, so I hope that you will find a good insights of the graphical deep learning, and our team will try out their best to share their insight and what is actually happening in this today's research, and how you can accelerate your research. So for that, we have Dr. Abhishek with us. So he's a pioneer in the graphical deep learning domain. So he has already experience for 13 years. So that will again Neha will let you know more about this thing. So I again kind of want to encourage our participant that to discuss in this particular today's session. So if there will be more discussion from this should be a two-way communication, so where we also want to know what are the different domains in which you people are working on, and what are the difficulties that you are finding. Fine. So it will be a again not kind of one-way communication. So we want to have your inputs also, right? So you can also mail us, or you can just write something queries if you are in the chat box, where so that we can better understand your problems. So you can always ask question in between if you have any doubt. Fine. And try to find your fellow attendees here. Try to network them, collaborate with them. Okay, so that is the basically aim of this today's webinar. And after this, if you find this more useful, then we have also organizing a one-day workshop where you will see how the implementation of this particular program is done. So today is kind of introduction thing. So if you want to understand better the implementation of this particular domain, right? So if you're finding it interesting, so we have also lined up a one-day workshop where you will see how this particular program is implemented. Fine. So let's dive into the graphs now, and Dr. Abhishek will take care for and Damris that is taking care of our research part. Fine. So let's again welcome you all, and I hope that you will enjoy this particular webinar. Fine. Yeah. Thank you.
Thank you, sir. Thank you for your kind words. Before we dive into the final presentations, I would like to remind everyone to participate in the poll if you haven't already. Moving forward, I'm pleased to introduce Dr. Abhishek Gupta, the director of scholarscollab.com. Dr. Gupta holds a PhD degree in 6G IoT coverage and serves as a consultant in machine learning and deep learning. With over 13 years of extensive experience, Dr. Gupta has made remarkable contribution across diverse domains, including computer vision, IoT applications, data management, recommendation engines, power system management, and microgrid controls. His expertise in leveraging MATLAB and Python for innovative solutions has driven significant advancement in these areas. We are truly privileged to have Dr. Gupta with us today to share his insights on how advanced technologies are shaping the future. With extensive experience in developing and deploying deep learning models, he will be presenting how graphical deep learning can assist in the diagnostic and treatment of patients using EEG images. His presentation will also highlight key challenges and opportunities in deploying these solutions at scale. Without further ado, I now hand over the proceedings to Dr. Gupta. Please join me in extending a warm welcome to Dr. Gupta. Please welcome, sir.
Thank you, Neha. So I'm audible, everyone?
Yes, sir, you're audible.
Great, thank you. So I welcome you all on to the behalf of Scholars Collab into today's webinar. As everyone has already introduced about the webinar, what webinar is actually going to do. But I would like to key highlights the point. Like, this webinar is not only about the implementation of graph deep learning into the field of medical. This is actually about to focusing on to the graphical deep learning. Why the graphical deep learning? Most of us have already heard deep learning, machine learning. But what is this graphical deep learning and how it differs from the conventional deep learning algorithms? So for those things, I would be delighted to share my experience and my knowledge about these things, like why nowadays researchers are moving towards graphical deep learning instead of conventional machine learning or deep learning, and what's the advantage and what motivates them to use graphical deep learning, and what are the fields where this application can show a significant improvement into the previous results. So coming on to that, initially I would be focusing on like how the graphs are being generated through the data, and then how that graph is used into convolutional network and advancement of the medical analysis. So I'm sharing my screen. Please acknowledge everyone if there is some glitch into the screen sharing. So everyone, is it visible? My change of the screen is visible, right?
Yes, sir. Screen is visible.
All right. So current slide is I am on that. What is the purpose of webinar? Like I already told, this webinar is particularly is the introductory webinar for the purpose of graphical deep learning. We are highlighting graphical deep learning because a lot of researchers and coming up research is focusing onto the graphical data analysis. Whatever machine learning algorithm we are targeting, that algorithm is efficient only when you are having structured data. If data is noisy, data is having some kind of like lack of information or less number of samples, and however advanced machine learning or deep learning algorithm we use, that is not going to give that much improvement which we expect. So 80% or 60% focus should be on to the data analysis or data structuring. So into that case, graphical data structuring is very hyped field. It is not new, although because into the previous we have seen the use of graphical arrangement into power distribution, into internet, and into finance sector also. Everywhere where you can think that graphical structure was always there. Our internet is possible today because of the graphical arrangement of the data. So it is not a new word or new methodology, but it is new into the deep learning. How deep learning has evaluated and how the improvement into the existing deep learning, existing conventional convolutional network is showcasing the significant improvement with the graphical data. So during this webinar, we would be focusing on discussing an IEEE transaction paper which is using EEG signal into the medical, and what medical field we are using, that is based upon the neurology. The depression detection is the primary focus of this paper, how the depression detection is improved with the help of graphical deep learning. So during this webinar, I would also request you and invite every participant to engage into the discussion also. Wherever you want to contribute your parts, or you want to have some doubts, then please go ahead without any wait to end this webinar. And since I'm sharing the screen, please feel free to switch on your mic and jump into the discussion without raising hand. So how your research will be benefited into this webinar? You would be able to accelerate your research into advanced graphical deep learning. And since we are using IEEE transaction paper, so it is a validated platform. Whenever a new researcher is or an experienced researcher is starting onto the new topic, and they are trying to explore more information or more research a contribution into a topic, then it should start with a validated and very well published journal paper. So IEEE transaction papers are very well known into their credibility. So during this webinar, I would be focusing on the transaction paper discussion, so that we are not diverted, or we are not discussing shallow research. It is having a high credibility. And as the ethics and ceremony of every webinar and workshop, certificate of participation is there. So going on to the main content, what is the depression problem? What this is the medical disease we are focusing on to this webinar. So how big is the depression problem? Why it is being considered? As we everyone know, after the corona phase, the depression cases have increased significantly, and not only into this phase, it was very high into the past also. A very rise into 1990 to 2017 is pretty much visible. It's 49.86%, which is very huge. And after corona, it's populated more. So this is very critical mental health issue, where we need to diagnose, because whoever is into depression, that can be near and dear one, but due to lack of awareness, or due to lack of unnoticing and busy schedule, these things go unnoticed very easily. And if we still notice, then the diagnosis and detection is also very typical, and it varies from patient to patient. A single diagnosis to a single patient cannot work for another patient. This is a challenging task with the doctors also. So how we machine learning scientists, we engineers, can help into the medical field? We can come up with the power of deep learning to help out the medical specialist. So how can we do? Before going ahead, we need to study how previous diagnosis is taking place. As we know, a very conventional research method is the questionnaire. We prepare the questionnaire, we take the survey, and based upon those questionnaires, some analysis is being done. So this is very conventional way. Specialized physician interviews are the conventional methods to diagnose the depression. After that, they rate the patient on various psychiatric rating scales like PHQ-9, BDI, HAMD. Out of those, BDI is very much common and widely used. And after that, a very modern technique is EEG data collection. EEG, as everyone know, is a electronic signal recording from the brain. It is non-invasiveness. It is non-invasive because no needle is inserted into the body. It is just like we place a sensor onto the brain, and we record the brain activities into electronic format. And the data collection cost is very low. So and it is very much proved into psychological and cognitive science also, that we can study the brain activities with the help of EEG signals. So it is very much we can say reliable and non-invasiveness and less cost method. Although this is not only the solution. After this, we need to consult with the psychiatrist to help them and to ease their task. So this is not only the solution, but it is to speed up the diagnosis and with the help of doctors. So basically, coming on to the EEG data collection, once we collect the data from the EEG, that is not only enough thing. We need to label them. As I have seen into the survey, most of us are well versed with the machine learning, and they are well versed with the Python and the implementation. So there is no need to quote me what is label, what is testing data, what is training data. It is very basic thing. So talking about the label, like this recording is of depressing patient, or this recording is of a normal patient. So this is the categorization of the data. This categorization of the data can be done only with the help of expert doctor. So easy data collection is done by the engineer, and with the help of the doctor into that field, a good categorization and good labeling is done. Until we don't have the accurate labeling, our machine learning model will not give the accurate result. So as I told earlier, fusion of engineer and doctor is required now to diagnose the and to improve the diagnosis into the medical field. So the knowledge of deep learning and the knowledge of doctor are now integrated into the graphical convolutional network, which is graphical deep learning methodology. During this webinar, we would be focusing on to this thing primarily. So what is the EEG data collection and how EEG looks after recording? So as you can see onto the screen, on to the left side, these are the EEG recordings. EEG recording doesn't require you to have a single sensor. These are the sensors which are placed onto the brain. So multiple sensors can be placed. 64 sensors usually are placed onto the head, and every sensor is having a different frequency to record. That's why we see the different signals of the channels, and they are as we can see onto the right, so left hand side, onto the left hand side axis of y axis of this EEG signal. Some English letters are there: FP1, FP2, AF3, AF4, something like this. These are the name of channels. These are 64. So different channels at different locations are identified. These locations are not randomly selected. These are selected with the help of expert psychiatrists, those who can identify the brain complexity and from where we need to record the signals. So this data is presented into the research paper itself, and the author collected the data from the University of New Mexico, and they have categorized the data onto the basis of BDI score, like which are having BDI less than 7. They are normal patient, and who are having BDI greater than 13, they are with the they are suffering from the depression. So based upon this psychiatric scale, this data is categorized and labeled, and 122 subjects were used for the data set collection, out of which 46 were depressed and having highest score on to the BDI. So coming on to the primary challenge into the depression detection using EEG, as it is signal, it is recorded electronically, so it is having different challenges. The first challenge is that when we are recording the EEG, the movement of the body is itself a challenge. As the brain moves, as the body moves, brain reacts. Brain reacts, then the electronic signal coming out of the brain changes. That is a challenge. The body should be still. Moreover, because we are surrounding by Wi-Fi, we are surrounded by the electromagnetic signals, a lot of electromagnetic signals. So those electromagnetic signals interfere into the recording also, because our sensor is also an electronic device. So it got interference from electromagnetic signals surrounding the patient. So that also could add the noise of EMG into the data. Except this, if patient is lying and we are collecting the data, but patient eye is moving, he is blinking eye, then that also add the noise. So EEG is having so many flexibility to diagnose, but collection of the data is typical, and a slight movement to the body adds the noise. So what to do? We cannot stop the patient from the movement. We cannot stop the patient from eye blinking, and we don't have any control onto the EM noise surrounding the patients. So what we need to do, being an engineer, we have to come up with a solution to filter the noise from the data. So how to filter the noise from the data? The paper has implemented few things. Whenever we are using the EEG signal, we extract the biomarkers, several biomarkers which are extracted at different frequency band. Those frequency band, we need to find out that which frequency band is robust and less susceptible to the noise effect. So as we can see on the screen, there are 4 frequency bands. These are 4 biomarkers basically, like delta, theta, alpha, beta, and gamma. Out of those, gamma is the promising biomarker and less affected by the surrounding noise and all those things. After extracting the biomarker from the signal, a bandpass filter is used, which also again remove the noise from this and then followed by notch filter. And we resample the signal to 200 hertz. Resampling is done just to make every channel output as the uniform and equal number of samples. So this is not much to concern. This is just a filtering and pre-processing step of the data recorded from the EEG. If you get the clear data, then we come onto the problem of extracting the features, and we come onto the problem of selecting the classifier to have the higher accuracy. Basically, looking at the broader side, we are only dealing with binary classification. Patient is having depression or not. But this is complex. This is complex because I give you an example. When we go to a doctor to have diagnosis of any kind of disease, doctor does usually some testing on us, and based upon his knowledge which he has gained during the time over several patients, he is diagnosing our illness. He is not taking the decision based solely on our test. Point to be noted, only single subject test is not the diagnosis ground. The ground is the knowledge which he has gained over 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 many patients. The 2 different things are there. Time is a factor which we call in our terminology temporal data. The data which changes with the time is a temporal data, and over many patients means many subjects he has analyzed, he has diagnosed many patients. So the knowledge gained through that time over many patients is the key factor of the diagnosis of coming unseen patient. All right, so that's why usually we prefer an experienced doctor for the diagnosis. The same thing applies into machine learning. Machine needs to learn the temporal data, like as long as the duration of the data you are giving to the machine will be happy. The algorithm would be happy to learn more. And the decision which we want, that shouldn't rely onto the single patient. It should have the analysis of multiple patients. That's why we are doing spatio-temporal analysis into this paper. Moreover, there is a challenge because why we are using graphical data. It is derived from the literature. So what drives us to use the graphical data? The thing is that into the previous work, many researchers have used convolutional neural network, simply convolutional neural network. CNN basically sees the data, a signal also as the image. If we are very much aware about the CNN, how CNN works. If not, then also I'll tell you. CNN only works in a grid manner. Like whatever CNN was initially developed for the images. So what it sees the data always as an image and divides the data into grids, several grids, and it applies the convolutional operation onto every grid. So, but the signal and specifically EEG is not a grid. It is collected from the various channels of the brain, like this channel, this channel, this channel, and this I am talking about a patient only. We are having, for example, 20 patients, and every patient is having 16 channel. Every 16 channel is having different recording, but a common label. So the challenge is that we are not previous work. If talking about CNN is only working onto a single channel, not considering and not taking any relational analysis with another channel. If I am applying CNN onto the EEG, then I will be applying CNN one by one onto this channel, then this channel, then this channel. The dependency of these channels onto each other and dependency of this or correlation of this subject to this is not analyzed. We are not exploring this. That's why the effectiveness of CNN is challenged over here. Now, CNN is okay, is not good, but what about other graphical methods? We are having GNN, graphical neural network, because this paper is claiming GCN. So, coming on to the GCN, we need to study what is the challenge with the GNN. Why, apart from GNN, GCN is selected. So, GNN, graphical neural network, it is again graphical deep learning, like GCN. But why GNN? Why not GNN? Because GNN is again lacking the temporal dependency. It is not studying the data over time. Nahi hai, temporal dependency is not there. Moreover, GNN is also not considering the dependency of, again, the subject's dependency. It is not considering. That's why GNN is not that much efficient into EEG specifically. GNN can be good into other application, but particularly into the medical analysis or any kind of like, for example, financial field like stock prediction, etc. GNN is not suitable because it is lacking into temporal dependency calculation. That's why we are finally, not we, the paper is finally selecting the GCN to extract the features from the EEG data. Now, how the features are extracted into EEG data? Okay, that I will be coming on to the later slide. Now, discussing finally the challenges in differential detection. The first one is that individual differences and dynamic connectivity between the brain networks. That is a challenge. And as we know, EEG and electric signal. So high randomness and nonlinear feature extraction is also a challenge for this. Likewise, the temporal information and time series analysis is also a challenge to analyze into EEG. So what is the solution? The solution is graphical deep learning. Why the graphical deep learning is a solution? Because as I told earlier also, these are the points. Graphical deep learning better represents the brain connectivity. It is also easy to develop an adaptive topology learning with the graphical deep learning, which can present a complex and hierarchical feature into a simple way. And that's why the simple classifier can also give you better accuracy than the complex deep learning methods if we are extracting the relational features from temporal and spatial domain using graphical deep learning. So how the graph between EEG channels look alike? Like we see there are the FP1, FP2 are the channels, or you can say these are the sensor names or the location names which are placed on two different locations of the brain. So these are basically like we see, if I say CP6 is connected with CP4. So what is the connection strength between them? What is the connection strength of CP6 with the F4? This can be calculated with the help of distance between the sensor placement. If anyone is onto the system, they can easily go on Google and search the EEG data collection process. They'll find the images with the brain covered with many sensors. So this is the way. Basically, you can say this is the different hemisphere locations onto the brain or onto the head where different sensors are being placed, and these sensors are having some distance between them. Like F4 is, we can say the position of F4 is defined by some coordinates x, y. Its position is defined by some coordinate p, q. Then what is the difference between these two sensors? It can be calculated by easily by simple your x minus p square plus y minus q square and square root. So this is the distance formula which we can use, and using this distance calculated between every sensor, an adjacency matrix is being generated. Adjacency matrix is what? It actually depicts which signal, or sorry, which channel is connected and how strong the connection is into a form of a matrix. Like if I plot a matrix, that size of matrix would be 16 cross 16 because the paper has selected 16 channels out of those 64. So those 16 channels, if we are calculating the distance between every channel to every other, So a matrix is generated of 16 cross 16. This matrix is called adjacency matrix, and it indicates which channel is having highest strength to which one. All right. So this is a simple representation which has been plotted through our code implementation. So do we have any question from anyone? All right.
Can we get the DOI of the paper?
Sorry, you're not audible clearly.
DOI of the paper, sir.
I'm sharing that, and paper has been already shared with the mail.
Yeah,
Okay,
I've shared.
thank you, sir.
You can check your mail also with the for the paper.
I have shared now.
So this is the paper. This paper was published in 2023 into IEEE transaction on neural system and rehabilitation engineering. And the prestigious author for this is Gang Liu. Although we have seen a major, you can see the contribution into graphical deep learning is coming from Chinese researchers and US-based researchers. And a very less contribution from other countries is observed into this contribution. Why is this happening? This might be due to the lack of, because graphical deep learning, when we are making the nodes of the data, that require higher computational. So that those governments are investing more onto the computer hardware. That's why these kind of things are more, you can say, this is just my assumption. It is nothing driven by the some sort of survey. All right. So leaving that, we are coming on to the topic. So this is exploring adaptive graph topologies and temporal graph network for EEG-based depression detection. This paper has described the methodology into 3 different modules. The challenge between GNN, which I told earlier, that it is not considering the temporal data. Alongside with that, a major challenge into GNN is that it requires pre-computed adjacency matrix to use. Pre-computed adjacency matrix, as the word indicates, pre-computed. It is not flexible enough to incorporate the knowledge or learning from different patients. If you are having data of 16 patients and you have pre-computed the adjacency matrix using the sensor locations of those patients, then you can first of all you can have the adjacency matrix from a single patient at a time. It cannot be uniform if you are using GNN for all patients. This is the major improvement done into this paper. It is proposing a uniform adjacency matrix which is calculated based upon the based upon the geographical distance as well as the correlation of every patient data. How they have done, I will be enlightening that part also. And after that, after this improvement of the GNN, they are calling this as adaptive graph topology generation. This is a module which is basically module where they are calling it adaptive graph topology generation, where they are improving the drawback of GNN. And then coming into that, after doing some pre-processing phase onto the signal of the EEG, they are coming into the model of graphical convolutional gate recurrent unit. Basically, that is the combination of 2 different methodologies, GCN and GRU. GCN, as we know, graphical convolutional network, and GRU is the gated recurrent unit. Because this paper is claiming temporal analysis plus spatial feature extraction. So temporal analysis or temporal feature extraction is done by GRU and spatial feature extraction is done by GCN. All right. So once they extract the features from GCN and GRU, after aggregation of those features, they are moving towards third final module, which is graph topology based max pooling and MDD prediction. So what they are actually doing into graph topology based max pooling, they are just selecting the relevant feature and bypassing the non-relevant feature with the help of max pooling layer, and finally using the fully connected layer as the classifier. So as I told into the beginning, the data processing is the crucial thing into deep learning. If your data processing feature extraction process is robust and very efficient, then a simple classifier can also give you higher accuracy. Likewise into the paper.
మీకు ఎక్స్ప్లెయిన్ అదే కావాల్సింది.
Is my PDF visible? I'm showing the paper. It is visible.
టైం ఎంత అయింది?
All right. So coming on to the first module, how the module is working. As we know, if we are collecting the signal of EEG, it is, for example, collected for 10 seconds. At the and after the uniform sampling, the frequency of the recording is 200 hertz. So basically, if the signal is recorded for 10 seconds at the frequency of 200 hertz, so it would be having very high number of samples. All right, 10 into 60. These will be number of samples of this signal. So what actually this is how this is being done, and this signal for a single patient are for 16 channels, and we are having such 16 channels for 64 patients or 116 patients, right? So this would be very high and very complex to handle such kind of data. If and moreover, if you want to extract the temporal dependency, then the signal should be sliced into different slices. That's why this paper has sliced every channel signal into a slice of 2 seconds. Sorry, into a slice of 3 seconds with an overlapping window of 2 seconds. So, for example, what does it mean? It is doing that if your signal is of this length, then for example 0 the time is t and this is the signal amplitude, then it is slicing this signal. This is a channel. I'm talking about a particular channel output, channel output, and it is slicing this into a frame of 2 seconds, sorry 3 seconds, and next frame is selected with an overlapping window of 2 seconds. All right. Likewise, it is doing this slicing for all data. Okay, so using this slice, what we are having now, a signal of 3 seconds, 0 to 3 into this slice, and then another slice, then another slice. This basically is one channel. Now every slice is processed through GCN plus GRU. All right. To process GCN and GRU, these needs an input. That input is the adjacency matrix. And the contribution of this paper is to create a uniform adjacency matrix, which can be input to every channel and every slice. So how they are doing this? This is very easy and very simple way they have done this, because the simple adjacency matrix between channels is calculated with the help of normalization of the distance, as I told you earlier also, like into the slide. How we can do this? This can be done with the help of this example. I have shown into this slice. Like FP2 is having some XY coordinate, F4 is having some PQ coordinate, then simple distance formula can be used to calculate the distance. So that is done over here. And now this is the distance between every channel. Now the paper is doing calculating the correlational matrix between every patient with the help of this formula. This is just Pearson correlation coefficient, and a common trainable adjacency matrix is used using the is calculated using the help of ReLU layer, and a correlation from equation 2 and from equation 1, a common, is used to calculate the adaptive ReLU with the uniformity. So why it is adaptive? Because it is getting trained with the correlation of every patient. That's why they are calling it as the adaptive graph topology generation and presenting it as the first module with this sliced EEG signal. Once you are having the graph, now graph is what why from where suddenly graph word is coming into the existence. This is slight EEG because once you are having the adjacency matrix, why we are calculating the adjacency matrix? The reason is that we need to create a graph. To create a graph, every channel is presented as a node. And how this channel is connected to every other channel is only presented or is only prescribed by this adjacency matrix. So basically, in terms of the visualization, we are calling it graph, but into the implementation of mathematics, we are calling it as a matrix. So basically, adjacency matrix is the graph. And why it is called graph? Every column is a node because it is having the 16 cross 16 size. Every column is equal to the some biomarker or you can some sensor which is placed onto the brain. So if there are 16 sensors, then 16 columns would be there crossed by 16 rows. So that's why we are calling adjacency matrix further a graph into the broad term and just for the visualization purpose. Like this paper has done into this module. After that, GCN is used. To study more about GCN, let me tell you, GCN is nothing more than the convolutional operation between the different nodes. So you can go through the paper of the GCN. I'll show you the GCN paper. It was published recently into probably since then there are a lot of uses of the GCN. It was published into 2016. Right. So for more detail about GCN, I'll advise to go through this paper and sharing the link of this paper into the chat also to the channel. This paper is basically presenting GCN or validating GCN as a first order approximation of the spectral graph convolution. So because whatever the convolutional operation is being done, that represent the spectral convolutional things. So GCN is also a spectral feature extraction process, and because several nodes are used into GCN, so first order approximation is used to simplify the convolutional process. So how to do convolution, that is a part of basic mathematics. And why the first order approximation is used, just to because there are various approaches to calculate the convolution between two numbers. So first order approximation is the simplest way to calculate the larger number of nodes convolution. So I am sharing the paper link also into the chat. Now coming back onto the main paper, screen is visible, the PDF is visible, right? So again, as I told earlier also into the third module, they are just aggregating the data. Aggregating the data means we are slicing the data, and these slices are just aggregated for all the patients. For example, if we are having 3 slices for a channel, then a patient is having 16 channels. So we would be having 16 cross 3 slices for a patient, and likewise we are having 116 patients. So these will be the stack of slices, one slice, second, third, fourth, fifth, this like 116. So basically what we call this segment as the feature of GCN plus GRU. This is the output from GCN plus GRU. Spatio-temporal feature are stacked over 116 matrix. So coming on to that, they are just doing applying max pooling to bypass the non-relevant features and applying the fully connected layer to classify the MDD and normal patient. So with the help of this methodology, they have done some ablation study also and compared it with the previous work also. We can see even after their so efficient methodology, they are able to achieve with the accuracy of 77.78 onto this data. This data is quite challenging, and with the help of this data, The previous works, like those based only on to convolutional network, they are having very less accuracy, 68.76. Like another convolutional network is having very less accuracy. Again this the graphical network is into existence over this paper, into this paper, into this paper. They are apart from this, they are having good accuracy, but F1 score is also good into these. So you can see this is the comparison. And apart from this state of the art, they have also presented the ablation study also. Ablation study, as you can see, as you understand, the various combination of these three modules. This is there are 8 cases they have presented of their work only. Into one case, there is no module being used, simply classifier is being used. Then they have dropped AGTG and GCGRU model, just GTMP module they have used. Then followed at the end, S8 is the finally proposed module where they have tested with these 3 modules into the implementation, and this is the accuracy they have achieved and F1 score. For this paper is published into ITB Transaction, and our team at the Scholars Collab have spent 5 to 6 months into the implementation of this paper. And Dr. Damaris was the key project manager to implement the this paper, and she has led the team of 3 Python developers. And at the end, we achieved this accuracy and was able to improve the accuracy from this paper also. So during the next phase of this webinar, I would also request Damaris, and Damaris will come on to the platform now. She will be mapping the implementation which we have done with the papers module, and will show what we have done and how efficiently it is implemented. And this code is, again, I am reminding, is available onto the onto our website, and the link is already shared into the chat also. So you people can go there and download this code free of cost. And we are inviting you all into the next upcoming workshop onto the 8th of December, where we would be presenting you the live execution and implementation of this code, and will help you by your handholding, so that you can reach with the same level of implementation. So whatever knowledge we have gained during the implementation of last 6 to 7 months, that implementation and that knowledge can be transferred to you within a day and with documented resources. So I would hand over the session to Neha again, so that she can handle the proceedings further. Meanwhile, if someone is having any kind of doubt or question, please go ahead without any hesitation in between the session also. So I would request Neha to please take over the stage.
Thank you, sir. Thank you for your insightful presentation. Proceedings with the session, I would like to invite Ms. Damaris Evelyn, a distinguished and a highly proficient biomedical engineer and a key contributor to the team at scholarscollab.com, to lead the code discussion. Ms. Evelyn brings substantial industry experience in signal processing, data analysis, and algorithm development. Her passion for leveraging innovative skills in healthcare and biomedical engineering has consistently driven positive change in the field. Ms. Evelyn will provide through an overview of a EEG dataset, elucidate the steps involved in code implementation, and offer a detailed explanation of the foundational methodology. So please welcome.
Thank you, Neha. Good evening, everyone. I'll just take you through the implementation of the code that we have done. So before that, I'll just explain about the steps involved in the code. We have done this in this paper. We have 5 steps involved. So those steps are, first we have to collect the data from the website, EEG website, and then we have to extract the data, which is encoded, and then process it. And we use the first module that is in the paper, that is AGTG module. And then we'll be going into the feature extraction method, that is GCGRU model. And then for the further node representation vectors and graph representations, we use the GTMP model. And finally, we use the fully connected layer to classify the classes of the project, like MDD and HC. So MDD is major depression disorder and HC is the healthy candidate. So moving further, so can you go to the next screen, sir. So moving further, we have collected the data from Open Neuro website. That is a website which collects EEG data for various reasons like Alzheimer's disease, EEG, depression detection, and so on. So we have taken the EEG data for depression detection, and which has 122 subjects data, and inside it we have the data encoded in encoded format, like FDT format and .set format. So to decode the data, we have to use the MNE library. MNE library is an open source library that is inside the Python resource itself. So using this library, you can analyze the EEG data, explore about the EEG data, and also you can visualize the EEG data that is encoded, that is in encoded format. So for after the data extraction part, we'll be going into the signal processing part. So for signal processing, we use the bandpass filter, notch filter, and then we use the resampling techniques and data augmentation techniques. So these were discussed by Sir earlier. I'll be showing the implementation of the code in the coming session. So after the signal processing is done, we'll be generating the graphs and the adjacency matrices that will be serving as the input data for the GCGRE model. So feature extraction is done using GCGRE model. It is a combination of GCN and GRE model. So GCN model will be getting the spatial features, and GRE will be extracting the temporal features from the data. So after that, we'll be using a GTMP model. So that will get the graph representation vectors and further differential features that can be extracted from the output of the features extracted. So using the GTMP module's output, we apply the final classification layer that will classify the subjects whether they have a MDD or HC. So from the feature extraction method, we use a library called PyTorch. So PyTorch is an open source machine learning library. That is a framework that's used for research and AI applications. So it is built on the Python programming language and the Torch library. So we have to import the library using pip install PyTorch, and then we can use it further. So let's go to the code implementation. Is it visible?
Not yet. Yes, it's visible now.
So initially, we have to import the libraries that we are going to use in the project. So those are Torch library, as I said, for the PyTorch library that is used for the feature extraction and other graph construction techniques. So from the Torch library, we'll be using the neural network model, that is GCN convolutional network and GRU networks. So after that, we use NumPy for basic mathematical operations, Pandas for basic mathematical operations, and these two, Matplotlib and Seaborn for visualization, and then sklearn for the performance of the model, to evaluate the performance of the model. So we have imported MNE library for decoding the EEG data. So going on further, we'll be implementing the paper. So first in the paper, they have implemented signal extraction and signal processing techniques. So in the paper, they have taken 16 channels out of 66 channels that is in the data. So this 16 channels can predict the depression detection accurately. So we have also taken the 16 channels that is specified in the paper, and we have given the functions for each and every step of extraction from the encoded data. So in signal extraction, we'll be using dictionaries to save the amplitude and the time, and we return the signal NP. This will contain the whole signal in the form of an array. So after that, we'll be using the participants file. The participants file will have the labels for the data, whether they have the depression or they are healthy candidate. So we have to extract that. And the main key feature of this paper is that they have a adjacency matrix creation that is very unique in this method. So for that, we'll be getting the electrode coordinates from the TSV file. There is a electrode.tsv file, so which has the XYZ coordinates of the electrodes. So we'll be extracting that also. And then we'll be extracting the labels and electrodes and the signal. So we'll be extracting the labels, electrodes and signal, and that process will be given in the output of this code. So after that, we'll be processing the signal. So as discussed in the overview, we'll be processing by using the filters, bandpass filter, notch filter, and then we resample the signal and we augment the signal. So data augmentation is it's discussed by Sir in the notebook. So where we have the signal in the form of a second wise. So we take 6 seconds of the signal as a window and 2 seconds of the signal as stride size. So it will split the signal into 6-second window, and then it will overlap that 6-second window by 2-second window. And we augment the signal, and then we have the signal stored in the form of a tensor. So why we store the signal in the form of a tensor? Because we use the PyTorch library that will accept the signal size in a orderly manner while we run the model. So we store the signals in the form of a tensor, and that will be the output from the signal processing step. So after that, we'll be extracting the labels, and we assign the labels like if the VDA score is greater than 17, they have no depression. If, less than 17, they have no depression, and greater than or equal to 17, they are having depression. So labels is assigned, and also we generate the adjacency matrix for each subject by calculating the Euclidean distance as discussed by Sir, and then we apply normalization techniques, and then we store that also in the form of a tensor. So we get the signal, the label, and also the adjacency matrices for each subject. So after that, we'll be going into the implementation of the paper. So first in the paper, they have implemented AGTG module. So in AGTG module, we have this generation of the graphs by using the signal and the adjacency matrices. So in this AGTG module, we have the signal as the input, and the adjacency matrices we created as also the input. So we perform the adaptive graph topology generation. So from that, we get the graphs of the subjects. So this graphs and the adjacency matrices will serve as the input for the GCN layer. So in GCN layer, we'll be applying the convolutional operations on the graph and the adjacency matrix, and we get the spatial features from the GCN layer. So likewise, we apply the GRE model, where we give the same signal and the adjacency matrices into the GRE model, and we get the temporal features as the output from the GRE model. And after that, we'll be having the GTMP model, where we find the highest node importance score and eliminate the other nodes that are of low importance, and which will accelerate the performance of the model and classify the type of disease in the efficient way. So we have the GTMP model implemented by applying the rank method that is discussed in the paper, and then we have the final fully connected layer implemented, and that will give us the output whether the patient has MDD or HC. So this is how we have implemented, and then we have got the same more improved accuracy than the paper, that is 83.5%, and we have achieved we have implemented other methods also, and we have got more accuracy than this. So I'd request you to go through the paper and analyze it, and you can also start coding by yourself, and then you have the free code of this project. You can experiment with that also by taking other channels and applying other bandpass frequency. Thank you for listening. Over to you, Neha.
Thank you, Damaris, for your insightful discussion. And now we are come to the end of this session. I would like to thank all of our esteemed speakers for sharing their invaluable insights into this fascinating topic. It's clear that graphical deep learning is paving the way for many innovation in healthcare, and this is just the beginning. As mentioned, we will be diving deeper into this field during the upcoming workshop, where we will go through the entire project in more detail. This workshop will cover everything from a literature survey to the full code implementation in Python. We will also provide a detailed explanation of how these algorithms work and you can apply them to solve real world problems. So the upcoming workshop will be held on 8th of December and we look forward to seeing you there. One more thing, we are offering an exclusive discount for the upcoming workshop. The original fee for the workshop is $499, but for those who make an instant payment today, we are offering a special discount, bringing the fee down to $99 only. And this is a limited time offer, and we encourage you all to take the advantage of this opportunity to join us for the workshop at the discounted price. For more details and to register, please follow the link shared in the chat section. Once again, I would like to remind everyone to participate in the poll if you haven't already. Now it's time to say final goodbye. Is anyone have a question?
Yeah, I want to have some feedback from you people. If someone want to share, if he or she want a particular research topic in which she is facing some problem, or in which field basically you people want to know more
Hello.
about. Yes.
Hello.
Yes, ma'am.
This is Dr. Sharani, Abhishek Gupta, Dr. Abhishek Gupta.
Yes, ma'am.
How much computational complexity is reduced if you worked with the GCN compared to CNN?
I would answer
Have
this.
you compared that?
There is no comparison about the complexity regarding CNN and GCN. Both are different on different aspects. Although if you directly want to know about the comparison, then GCN is more computational complex than CNN.
No, that's what I observed. That's why I'm asking.
Because it is
Parameter wise, is there any reduction in the computational complexity?
parameter are less. Tunable parameters into GCN are very less compared to CNN, because what CNN does into multiple layers, that GCN does into single layers, and it doesn't require the different strides like CNN doesn't require the different window size like CNN require. So parameters are very few compared to CNN, but it is complex because of the contribution of graphical structure. As the nodes increase, the computational complexity increases into GCN, but because these are both these algorithms are on two different grounds, so directly not comparing into any paper.
Here you are combining spatial as well as the temporal aspects.
Right.
Is it the same as our LSTM plus CNN? In the same way you are doing LSTM?
Conceptually, it is same.
GRU and GCN.
Yes, conceptually, spatial and temporal, meaning that we are extracting the spatial features as well as time domain features. So
here you are extracting the features, you are feeding the features to the network, not the images.
Right. Apart from this difference, the major difference is that features are being extracted spatially with the help of graphical presentation of the data. So relational analysis is being done. And if we remove the graphical analysis, then it would be conventional CNN plus LSTM.
You are applying this to the medical thing. Is it applicable to agriculture data? Where
Yes.
also we want to study the spatial as well as the temporal aspects.
Yes, yes, ma'am. Yes, it is applicable over there. Recently, we have experimented with the crop yield prediction also with this GCN application along with the GRU. That also gave us very significant improvement instead of CNN and other regression analysis. So
Okay, thank you.
it is very useful for that. And into the next upcoming workshop, we are focusing on to the implementation of the uses of GCN into various data. We will be using that GCN onto the financial data. We will be using GCN onto the your agriculture data, and we will be using GCN into this EEG data. So these three fields will be tested for the GCN and the what is the accuracy and what is the improvement over conventional CNN or regression analysis. That would also be tested into the upcoming workshop.
Is it a one-day workshop?
Yes, it's only one day workshop and it will be from 2 to 3 hours. So it's not going to take much time. And since 8th December is Sunday, so I hope we all would be available to join the workshop on Sundays if we are not having some personal emergencies.
Thank you.
All right. So basically, into the workshop, it would be like handholding session and will taking you through the different application of GCN into different domains, so that we all from different domains can club into a single research pipeline. All right. So that's why I motivate you all to join this workshop. Although this is not completely free, it is coming up with the little cost of 99 rupees plus GST. So that's just for the motivation of our team also, right? So and this 99 rupees is only for today, and then after today the price is again normal 499 plus GST. So the fees is very much nominal, just to motivate the in-house team of Scholars Collab, and it is the workshop that would be very much helpful to go ahead, whether we are researcher, whether we are engineering graduate, whether we are PG students, whether we are faculties, professor who are working towards and exploring the research field into the graphical data, everyone would be benefited into that workshop. So any okay, Uday, I'm again telling this workshop would be more focusing on to the uses of graphical convolutional network into the field of financial, into the field of medical, into the field of agriculture. So three different data sets will be tested using GCN and will be compared with the simple regression analysis, that what is the improvement we can see over these things.
Sir, how many the workshop is?
Sorry?
Workshop timings and day. What are the
Day
date?
is day is 8th December, and
8th
time would
December.
be probably into early morning hours, like 11 to 1 or 11 to 2.
Okay, duration of the workshop, sir?
3 to 4 hours. Maximum
Here
up to
you
4
are
hours.
showing 2 hours.
Maximum up to 4 hours, 2 to 4 hours it would be, but we are maximum 4 hours would be there. It won't be more than 4 hours. It can be lesser, but it will not be lesser than 2 hours.
Okay, sir.
Yes, the GCN is also very beneficial into the field of wireless sensor network also, and into WSN particularly in security side, it would be helpful, and it can be helpful into the security side where we are trying to identify the intrusion detection into IoT also. Alongside it is useful for the clustering also. And if we are working into, because there is some question from our participant whether we can use into wireless sensor network. So we can show the uses of WSN also, because GCN is very good into the clustering part, into organizing the data. So just by using the random data, we can show how much accurately and efficiently it is clustering the data compared to the k-means or other spectral clustering approaches. So we can show this too into workshop. It is this clustering presentation will not take more than 5 to 10 minutes with the help of GCN.
That workshop application to healthcare domain. So can you share more about that? How healthcare domain applicability will be there in that workshop on that 8th?
There would be a discussion of the implementation of the current paper which we have discussed today into the webinar.
Okay, only today's paper will be
Yes,
briefly
only
discussed in
today
the
because
healthcare domain.
yes, because the into this small time we can only use the one kind of data, only a single EEG signal we can use, and it's a very we are selecting this because this data is very much complex. There are many data sets available onto the depression detection using EEG. They all are able to have higher accuracy, more than 95 96% with the conventional deep learning algorithm also. So they don't impose any kind of complexity into this sector. But this data, which is realistically and collect with the some many noises, this is posing challenges to other algorithms. So that's why this is challenging data set and good to use. And moreover, when we are going to research improvement, we should select those papers which are using challenging data sets so that there is some scope of improvement. If we are going already behind that 99% accuracy data set, then there is no room to improve. Right. So let's meet into the workshop on 8th December. And meanwhile, if there is any kind of query and requirement, you people are having our email and phone number into your emails. So we can you can be in touch anytime. We can answer your calls during the office hours onto weekdays, and we can reply your email anytime. So please do feel free to ask any query regarding this webinar, regarding any kind of research, regarding workshop. We would be happy to answer.
Sir, okay, sir. Thank you. Sir, I have one doubt. Sir, can we use the same code and for the and different data for publishing a paper?
That depends. We won't say that we won't claim actually that this code will be working with your data. You need
No,
to
sir.
make some adjustments.
Yeah, I will make some adjustment, but using basic of this, and if I develop on that, and I can publish a paper, and I can do on my own data, right, sir?
Yes, you can use the code, but regarding publishing of the paper, that I cannot say anything about that because that will mainly focus on your contribution, like what exactly you are contributing into you. But the basic pipeline of this paper methodology that can be used to develop some improvement with your data.
Okay, sir.
Right, like I give you an idea. It is using subject-wise relational analysis. So you can make a network which can be the fusion of subject-wise embeddings and channel-wise embeddings. So you can make some population-based brain network. So these kind of things we can do, but I don't think exactly following the same methodology with different data will be a kind of contribution from our side.
Yes, sir.
All right.
Thank
So
you.
see you everyone into the workshop, and I hope we can meet again on 8th December. Most of us we can meet. All right.
Sir?
Thank you. Ji Dhanusha.
Sir, whether certificates are provided for this webinar, sir?
Yes, certificate will be mailed on your email.
Okay, sir. Thank you, sir.
Okay. Thank you everyone for the joining, and I hope this session brought some kind of information to your research area. And we also enjoyed connecting with you, and we'll keep this journey going on and more focusing on to the graphical deep learning and contributing into the research academia, and we'll keep on moving ahead into this field. Okay, thank you everyone. Have a good night. Bye-bye.
Thank you, everyone. Good night.